It's Murphy again. So listen, we are now starting stoichiometry. All right. You need to not take this lightly. Do not let it seem harder than it is. It is nothing more than a molar conversion wherein we add one step. That's it. That's it. But if you never learn molar conversions, then this is not going to work for you. Okay? So I'm going to share my screen. Stoichiometry, center of chemistry. It is how chemists solve problems in all different genres: gases, solutions, acids, bases, regular everyday reactions. Stoichiometry is nothing more than using ratios provided by balanced chemical equations to determine relative amounts of reactants and or products in a given reaction. So if I need to produce a certain amount of product, I will use stoichiometry to figure out how much reactant I should use. It's just like cooking in the kitchen. If I need 10 pieces of chicken and mashed potatoes for 10 people, then I'm going to figure out how many potatoes I should use and how much chicken I should buy. It's stoichiometry. If I want to double my recipe for making cookies, then I need to double all of my reactants. Stoichiometry. It's just like cooking in the kitchen. You know you have a stoichiometry problem when you are given information about one substance and asked for information about another substance. When that happens, you know you have a stoichiometry problem. And in order to solve that stoichiometry problem, you must have a balanced chemical equation. Once again, when you are given information about one thing, sodium, and asked about another thing, magnesium phosphate, sodium chloride, chlorine, you have a stoichiometry problem and must have a balanced chemical equation to solve that problem, period. If you are given information about one thing, sodium, and asked about that other thing, sodium, that is not a stoichiometry problem. That is a molar conversion, more than likely. Okay. Periodic table, calculator, participate. All right, I'm going to share my screen now. I'm going to share my screen here. Here we go. Okay, stoichiometry. This is chemistry all day long, okay? All day long chemistry. Stoichiometry, we use it all the time. It falls into the process of solving many problems. So let's start with, let me get some line on my paper here. That's a little, yeah. I hope you guys are okay with this color I have chosen. And let's see how this color works on it. Yes, that should work fine. Okay, big word. Okay, stoichiometry, it is the study of relative amounts of reactants and products. I try to, sorry if I write too long. Reactants and or products, okay? Requires a balanced chemical equation. As we just said, that is very important for you to realize. You must have a balanced chemical equation to solve any stoichiometry problem, period. You know you have a stoichiometry problem when you're given info about one substance and asked in a reaction and asked about another in the reaction. Okay, so that means I have a stoichiometry problem. Stoichiometry problems differ by way of what you are given and what you are asked for. So the first type of stoichiometry problem, which is the simplest type of stoichiometry problem, is a mole-to-mole stoichiometry problem. But it just occurred to me that before I do that, we need to continue our discussion of this. When I have a balanced chemical equation, say that my balanced chemical equation is nitrogen plus 3 hydrogen yields 2NH3 ammonia, all of which are gases. This is actually a very common reaction. There's a name for this, the Haber process, the formation of ammonia. Ammonia is used in fertilizers, so we need to make it, okay? And what they may say is how many grams, right, of ammonia can be formed. Let me not do that yet. What does this equation tell me? Well, it tells me several things. It tells me that 1 mole of nitrogen, so you're in the kitchen, 1 mole of nitrogen relates to, for every 1 mole of nitrogen, I'm just trying to think of how I want to say this, right? I would need how many moles of hydrogen? Well, remember, mole is an amount. You can measure it by getting the masses. So if you need 1 of these, then you need 3 of these in terms of moles. So 1 mole of nitrogen to 3 moles of hydrogen, or 3 moles of hydrogen to 1 mole of nitrogen, right? These are called mole ratios. We get them from using the balanced chemical equation. And it is the centerpiece of stoichiometry. You must have a balanced chemical equation because the balanced chemical equation gives you the mole ratio between the two substances you're talking about, okay? So we've got some other mole ratios in this balanced chemical equation. I could relate hydrogen and ammonia. I could say that for every 3 moles of hydrogen, I used 2 moles of ammonia will be produced. Or I could say, in order to produce 2 moles of ammonia, in order to make 2 dozen cookies, I need, according to my recipe, 3 moles of hydrogen, right? It's just a recipe, which gives us ratios. There are 2 more ratios provided in this recipe, and that would relate nitrogen to ammonia. So if I use, because it's a reactant, it gets used. If I use 1 mole of nitrogen, then how many moles of my product, NH3, will be formed? 2 moles NH3 will be formed. Or in order to form 2 moles of ammonia, I need precisely 1 mole of nitrogen. All right? Those are the centerpiece of stoichiometry. Now, the steps you take, just like in molar conversions, depends on what you're given and what you're asked for, okay? We're gonna do the first type of stoichiometry problem, which is a mole-to-mole stoichiometry. It is a 1-step problem, all right? You are given moles and you are asked for moles. You're given moles of one substance, asked for moles of another substance, stoichiometry, mole to mole, one step. So let's say like this. In a reaction, right? I want you to have to actually write this problem. In a reaction, 0.345 moles of magnesium reacts with, what do we want magnesium to react with, guys? Let's keep this simple. Magnesium reacts with let me think of how I want this to work. No, I don't want to do that. Yeah. Oxygen. How many moles of oxygen react? How many moles of product formed? Okay. Well, let's look at what we're given. We're given 0.345 moles of magnesium. All right, 0.345 moles of magnesium reacts with oxygen, that's plus O2, yields magnesium oxide 2. I've got my balanced chemical equation. I am given 0.345 moles of this. I encourage you to write that down, right? So I'm like, okay, I've got my equation. Now I'm going to keep very organized. And what do I have? I've got 0.345 grams. No, whoa, big mistake, moles. So make sure that you include the unit that you have, because remember, it's the units that are going to tell you what to do. First question that we are asked is how many moles of oxygen react? So I'm going to go right here and go question mark moles. So you see I'm given information about magnesium. I'm asked for information about oxygen. This is a stoichiometry problem. I need to get from magnesium to oxygen. I do this by using the mole ratio, right? That's how I get from one to the other. What do you always start your T-chart with? You always start with what you're given, right? We still do that. Well, what are we given? 0.345, 0.345 what? Moles of what? Magnesium. The more you label, the less mistakes you'll use. Draw your T-chart. Same rules apply. What needs to go on bottom? What we have, our unit that we have. What are we looking for? Well, we are going from moles of magnesium to moles of oxygen. I can use that by using my mole ratio. So I'm going to write moles of O2 up here. I'm then going to look at my balanced chemical equation, and it is a 2-to-1 ratio. So for every 2, let me get my color back, magnesium, oh, I made a mistake. This is just mg, my bad. Every 2 mg's, I need 1 m2. That probably confused you so much. So sorry. Oops. This cancels, this cancels. I'm left with 0.345 times 1 mole of oxygen. Those of you that have been paying attention, you know that I would not times it by the 1, divided by 2 equals 0.345 divided by 2. And that is 0.173. 0.173 what? Moles of what? Oxygen. I need you guys to get, some of you to get better at that, okay? We had another question. It said, how many moles of product formed? So that means we're being asked about this. How many moles. So let's go from what we know, this, to what we need, this. Start with what we have, 0.345. What? Moles. Moles of what? Magnesium. Take what we have down here and what we need up here, right? How do we get from one substance to another? We use our mole ratio. This time it is 2 to 2. Those will cancel. We'll end up with 0.345. What? Moles. Moles of what? Magnesium oxide. That will be produced. And this here will be consumed, used, right? It's a reactant. Okay, well, what if it was not a mole to mole problem, right? What if it was not mole to mole stoichiometry? Now, you may want to stop and walk away for a minute, right? You might want to pause and walk away for a minute. Maybe not. Maybe it is mole to mass stoichiometry. All right. Well, let's say that we have, just trying to come up with a reaction. Let's go back to our N2 plus 3H2 yields 2NH3. All right. Let's say I'm going to write that down here, and I'm going to write the question on top of it. How many grams of product produced if, let's see, moles. So I need to start with moles. 0.762 moles of hydrogen reacts with, reacts with excess nitrogen. That word excess means don't worry about it. It means you have a lot of it. It means that the hydrogen is, you only have a little bit of, and it's going to run out. And when it runs out, the reaction stops. So let's look at what we're given. We are given 0.762 moles of hydrogen. So I'm going to write that right here, right? 0.762 moles. And then I'm going to look at what I'm asked for. And I'm going to see how many grams of product. So that's a mass of product. So I'm going to write question grams here. So I see that I have stoichiometry. I'm given hydrogen. I'm asked about ammonia. I need to go from here to here. I do that by using my mole ratio, which is 3 to 2. And I always start my T-chart with what I have. Moles, moles of what? Hydrogen. All right. Draw your T-chart. What has to go on bottom? Moles of hydrogen. Well, think about the end game. We need to get to ammonia. A mole ratio allows me to go from here to here, right? A mole ratio takes me over there. If I have moles, the logical step is to go ahead and get to what I need, right? By looking at the ratio provided by my balanced chemical equation, it is 3 moles of hydrogen, right? So I'm even going to highlight this to every, I'm going to change my color to every 2 moles of ammonia. So that's what's going to go there. All right, I'm done with hydrogen. I used my mole ratio to get from one to the other. I now need to convert to grams because I was not asked for moles of ammonia. I actually need to know the grams of ammonia. This is simply a molar conversion. 1 mole of ammonia has what mass? Well, we need to add that up, and that's going to be 17.04. I just know it, all right? Now let's get our answer. 0.762 times 2 times 17.04 equals, divided by 3 equals, I've got 8.66. 8.66 what? Grams. Grams of what? Ammonia. All right. So that was your mole to mass. There's 2 more. This time we're going to go mass to mole. All right. So you're going to be given grams. You're going to be asked for moles. Let's use our equation. Go back to, how about, I don't know, why can't I not think of anything? I can't think of anything. Let's do CH4 plus O2 yields CO2 plus H2O. We're going to need a 2 there and a 2 there. Let's make our question say, how many moles of oxygen are required to react with 12.4 moles of methane. Okay. Oh, sorry. And this needs to be a mass. This needs to be a mass. This is mass to moles. So let's say 120 grams of methane. Methane is CH4. Okay. So let's look at what we have. How many moles? Shoot, I totally messed this one up. Of O2. All right. How many moles of O2? So that takes us here. And that is question mark moles, right? Are required to react with 120 grams of methane. So we'll put that right here. All right. Okay. So once again, you see we've got a stoichiometry problem. We're going from here to here. And we do that by using a mole ratio. All right. So let's look at what we start with. We always start with what we're given. And that is 120.0 grams of what? Methane. We need to get from methane to oxygen. I use that by using my mole ratio. I can't use my mole ratio until I have the units of moles. So I'm going to convert my grams of methane to moles of methane, right? This is a molar conversion, so I'm going to say 1 mole. Methane has a molar mass of 16.05. Okay, periodic table. Now that I'm at moles of methane, I can use my mole ratio from what I'm given to what I'm asked for, and my question mark is over oxygen. So I will go to oxygen. And this is a 1:2 ratio. I now have moles of oxygen. I was left for moles of oxygen. So I'm going to get my answer, which is 120 times 2 equals divided by 16.05 equals, and I have 14.95. 14.95 what? Moles of oxygen will react. Okay? All right, last one is going to be a mass to mass stoichiometry problem. All right, let's go back to our nitrogen plus 3 hydrogen yields 2 ammonia. All right, let's make a question. Let's say that you need to know how many grams of nitrogen are required to produce, to react with, and let's say that we've got 100 grams of hydrogen. Okay, so once again, let's just look at what we're given. We've got 100 grams of hydrogen, so let's go to our hydrogen and write 100 grams. And we also have how many grams of nitrogen? So there's our question mark, grams. So we always start with what we're given. That's 100 grams of what? Hydrogen. Draw your T-chart, right? What goes on the bottom? Exactly, grams of hydrogen. What are we converting grams of hydrogen to? Well, think about it. We've got to get from here to here. How do we do that? Same answer every time. We use a mole ratio, okay? I can't use the mole ratio if I don't have moles. So I need to take my grams and I need to turn them into moles. So on top, I will write moles H2. This is a molar conversion. 1 mole of H2 is 2.02 grams. It's diatomic. You need to add up 2 of them. We're done with grams of hydrogen. Why did we take our grams to moles? So that we could use our mole to mole ratio. Moles of what? What we have, to moles of what? What we need. Look at your balanced equation. What I see is for every 1 mole of nitrogen, there are 3 moles of hydrogen. All right, I get that from looking right here, 1 to 3, okay? Now look at what we need. We need grams of nitrogen. So I need to take my moles of nitrogen, and that's N2, and convert them into grams of nitrogen, which is N2. This is a molar conversion. We put a 1 here. You go to the periodic table, you add up 2 nitrogens, not 1, you get 28.02. You notice that you have the unit that you need, you stop, you do the math. 100 times 28.02 equals, divided by parentheses, 2.02 times 3, close parentheses, equals, and I've got 462.4. Pay attention to your significant figures. And that is what? Grams of what? Nitrogen. That's stoichiometry, guys.